Okay, so welcome everyone. Thank you for attending and good morning again to those who are now joining us. So today we will be continuing with our discussion of these special signals that we started talking about last week, right? And of course that peculiar, what shall I say, um, invention called the unit impulse. Now, strangely enough, the impulse, you might be asking yourself, well, when am I likely to encounter something like that? I mean, it's defined by that bit of maths below there. It's not, it doesn't really exist in a practical sense because the area is one, yes, but the width is 0 and the height is infinity. So we define it as having an area of 1, and you could probably consider it as like an energy of 1 if you like. Now, where you encounter those, or where you are likely to meet an impulse, if you think about it, a type of impulse would be, for instance, a sudden blow to an object, or you have a system, let's say a vehicle, for instance, and the system and the car gets into a collision. At the point, what will happen to the vehicle or the occupant, for instance, is that you experience an extremely large deceleration because you were moving at a particular speed, and you experience a very large deceleration, and then you nothing happens, right? So at one point you have no acceleration, a sudden change in acceleration, and then nothing again, nothing again. So that kind of behavior is impulse behavior. And how does well, not only the human being, but how does the system around you, the car, the protective systems, how do they react to that type of impulse? Another impulse would be, for instance, you have an electronic system, and you plug it in, you turn it on, so you apply power, but as it turns on, the power fails. So you get a spike in power, and the power goes back down to nothing again. So what you have just done is to subject the system to an impulse on the power supply. How does the system respond to that? Now, those are practical impulses. And as we will see, if you test the system to the theoretical impulse, which is what we're talking about here, then when it actually is subjected to a practical impulse in reality, then the system, if it was designed properly, then it reacts as it should, and the behavior is as it was predicted to be. Yeah. So again, just the property of the impulse. Remember that the area under the impulse is important, not the what do you call it? Not the shape or the height, right? But the actual weight of it. And you can probably think about it like in the context of your weighted GPA, right? So it's an average of the sort of energy in the impulse, and we have this little integral below here that we define it as. So one of the important things that we saw last time is this thing called the shifting property of the impulse. And the importance of the shifting property is that if you take any function, and you multiply it by an impulse, and then, well, okay, and you take any function and you multiply it by an impulse, what it does is that the result of that process is to sift out or select the value of the function at the instant that the impulse occurred. Now, for when you're looking at the impulse, this thing here, this integral bit here, right? Forget the GT, for instance. Let me put a little line here. The integral and the delta part, that is the actual impulse itself, and that is equal to 1. But the 1 only occurs at the point T1. So if you multiply something that is 1 only at a particular point in time, then whatever the function is, you could care less what the function is. All it is going to do is to select the value of the function at that time. And we call that the shifting property. Yeah? And we could use that to explain sampling. You remember we mentioned sampling before. And it's very easy if you think about it now in terms of the mathematics. We explain sampling using a switch and a capacitor early on. Mathematically now, this is how it works. And you need this because later on, when you're doing things like signal processing or when you're talking about sampling and microprocessors and so on, you will hear them talking about this sampling interval or the sampling function and so on. This is what it actually looks like. So the thing about it is, of course, as we did last week, if you shift signals around, where the signal actually is determined by the index inside of here, right? So delta t is at t equal to 0. Delta t minus 4 is at t equal to 4. Yeah? Delta t minus 5 would have been t equal to 5. Delta t plus 5 would have been t equal to, come on, stop sipping your coffee. Delta t minus 5 would be the delta at where? Anyone? Delta t plus 5. Minus 5, right? Good. Very good. Good. So people are, at least some people are attending. So delta t plus 3, for instance, is at t equal to minus 3. And luckily enough, if you have a little slide here, once the delta, once you have the delta t minus tau, right? If tau is greater than 0, then the delta to the delta greater than if is, so if tau is positive, the delta moves this way. If tau is negative, then you have a t plus something and the impulse moves the other way. Right, and this figure here, if you zoom it up, are some examples of it. You can always change the magnitude of the impulse. Right, so for instance, this one has a magnitude of 6. So it means that instead of a unit impulse, it has 6 times the energy. Okay, this one is an impulse at t equal to 5, and it has an energy of minus 2. The amplitude has been reversed. And you could do that by just simply sending things through amplifiers and the like. So nothing too unusual about that. The energy of it is what is that constant in front of it. So 4 delta t is a unit impulse whose energy is 4. But the behavior is as all the other unit impulses have been. Let's just look at this, for instance. If you have, let's see if I could zoom this a little bit. Right, so the first one is that we have one, which is a 3t. You have x1 here, right, which is 3 delta t minus 0.5. So that means that the impulse itself occurs at 0.5 seconds, right? And the amplitude is 3 units. So it's a 3 unit. If you want to draw it, you draw it as an arrow, and the height of the arrow is 3. x2 is 1 at t minus 1. The amplitude is 0.5. x3 is an impulse at t minus 1, and what do you call it? The magnitude of it is 4, and x4 similarly is minus 1.5 at that point. So if you look at them here, x1 plus x3, or x1 and x3, however you want to look at it, they're both impulses, and they occur at different times. So one occurs here and one occurs here. So at different times, nothing happens in between them. So if you say x1t plus x3t, you add in 2 deltas, it doesn't matter. They are different times, so all you would have is 2 deltas. Look at x1 and x4 though. x1 occurs at t equal 0.5, x4 occurs at the same t equal to 0.5. One is 3 units positive, the other one is minus 1.5 units or 1.5 units negative. So both of them occur at the same time. So therefore x1 plus x4 will be a net positive 1 and the height is 1.5. Right? And then here's a little, to throw some things into perspective, here's a little a function here. Get a different color. Here's a function zt. The function is for t between 0 and 2, it is 3t. For t between 2 and 4, it is minus 3t plus 12 and is 0 elsewhere. So in fact, it is this little triangle function here. So x1, which is a delta here, plus plus zt, sorry, which is that triangle here. You plot the two of them, notice that it is a plus sign. So the shifting property, remember when we had the shifting property? Go back here. When you multiply, not when you add. So we go back here. This one here, x1 plus zt. So we're just adding the two. So all you do on a graphical display, you have the impulse, which is the blue line, and you have the blue triangle, which is zt. That's all. The real fun now starts when you start to multiply the signals around. This one is just explaining, this particular slide is just explaining what we said before. When signals occur at the same time, that's the first thing. And then what's happening now if we multiply the signals with the particular time domain function. So let me get that here again. So we have zt here. Look at the first one. x1t multiplied by zt. Where does x1 occur? At t equal to a half. So what it is going to do is to sift out the value of zt. It's going to sift zt at t equal to a half. You draw the graph, and at t equal to a half, zt will be 1. But 1.5 and the delta has a value of 3. So 3 by 1.5 gives you 4.5. Yeah? Clear enough? x2 by zt. All right, x2 by z. Okay. So backing up a little bit. We have this particular one is x1t multiplied by zt, right? x1 is an impulse of weight 3 at time equal to 0.5, at t equal to 0.5. If you multiply x1 by z, the shifting effect or the shifting function of the delta now becomes operational. So I'm multiplying x1 by z, which is what the function here is telling me. So what it is going to do is to sift out the value of zt at the point where the impulse occurred. The impulse occurs at t equal to 0.5. So at t equal to 0.5, what is the value of zt? It will be 3. It will be 3 multiplied by 0.5, right? Which is 1.5. So a unit impulse picking out a value of z at at t equal to 0.5 would pick a value of 1.5. However, the impulse has a weighting of 3. So it's going to, in addition to everything else, it's going to multiply that by 3. 3 by 1.5 is 4.5, which is the answer here. Yeah? Fair enough? Everybody following that? Nice. And similar things happen if you do x2 by z. X2 now is an impulse of amplitude -5. Right, so let me just clear these things here. So x2, and zoom up here now. X2 now has an amplitude or a weighting and energy of -0.5. So whatever this particular impulse sifts out, it is going to multiply this value by -0.5. It occurs at t equal to 2. So it's going to pick out the value of zt at t equal to 2. At t equal to 2 inside of here, that is right at this point here, the upper limit at it. So at t equal to 2 is going to pick out the value of 6 and multiply 6 by -5. So it's going to give you a value of -3. Yeah? And x3 now and zt, notice where x3 is now. Right, okay, this is where we, that's a good point. If they, okay, so to answer that question, the question was, at the point t equal to 2, should we, I am using this expression here as against this expression here. Remember the function, all right, let me clear that a little bit. Remember the function is doing this. So we have the impulse right at this, we have the impulse right at this point here. Exactly at the peak here. So what do we do normally is that if I am telling you that because everything is changing at the point, mathematically we say that it will change exactly at the point. So that t equal to 2 is right at the point before it changes from going positive to going negative. The actual value of the function here, if you plug this in here, the actual value of the function still is 6. Remember, it's not a discontinuous function, it's doing that. So whether you go just before or just after, zt is 6. I sample that and then I multiply by -0.5. We'll see a little bit later on in this same lecture about discontinuous signals. We might get to there in a short while. All right? And then the last one now is x3 multiplied by zt. Now, where does x3 occur? x3 occurs at t equal to -1. x3 occurs at t equal to -1. If you look at our function z at this point, does not exist. That function does not exist at anywhere less than, for t less than 0. Okay? So you have an impulse at t equal to -x4 is where it is. X3, sorry. x3 is at t equal to -1. So x3 is across on this side somewhere. Z is all on this side. So if you multiply the two of them, at no point in time does the delta function intersect or share common time with the zt function. So there's no answer, right? So there will be no sample at that point in time. All right? So all you have to do basically when you're confronted with any of these kind of things is to look at the instant of the impulse and to look where the function is defined. Right? Where defined. And that gives us now an idea of how we can explain mathematically what sampling is. Here's this little function, pt, and it is, if you run this, it is a sum of a series of impulses, right? So if you run this, let's just say for argument's sake, we run it n equal minus 2 to plus 2, okay? What that is going to give us is delta t plus 2, okay, plus delta t plus 1 plus delta t plus delta t minus 1 plus delta t minus 2. Yeah? So in other words, you're going to have 5 impulses. If you're running from minus 2 to plus 2, you're going to have 5 of these impulses. At t minus 2, minus 1, 0, 1, and 2. Okay? So similarly, if we extend n all the way from minus a very big number to all the way to plus a very big number, what you get is a series of impulses uniformly spaced apart, and the spacing is t, whatever capital T is. Could be 1 second, could be 1 millisecond, could be 1 day, it doesn't matter. This particular thing is what they call an impulse train, right? So it's a line, a whole series of impulses uniformly spaced apart. They sometimes also call it in some books called a comb function because it looks like a comb, right? I mean, use your imagination, right? It's a comb. So this now is an impulse train, and the thing is that this is what I use to sample. If I was to take this and multiply it by some continuous time signal f of t, that's supposed to be a t in the brackets. If I do that, and I mean, just let's talk about it before I put up the slide. If I take this now, get a pen, right? So take this and multiply it by some signal. I have to write bigger for this to work. Some signal f of t, which is continuous. What do I get? Well, we know that from the properties of the impulse, each of these, every single one of them is going to pick out a value of f of t at that particular point. So by doing this, if I take this whole impulse train function and I multiply it by some signal, what it's going to do, it is going to pick out or sift out, remember that's the key here, it's going to sift out all of the values of f of t that occur at the same instances of the impulse. So I'm going to get, again, if I were to run it for the minus 2 to plus here, and I multiply that, I took this and I multiplied by my f of t, it is going to give me f, whatever f was at minus 2, plus f minus 1, plus f at 0, plus f at 1, and plus f at 2. Fair enough? Make sense? Very good. So if I now extend the limits all the way negative and all the way positive, it is going to pick up all the other f minus, f minus 4, f3, 4, 5, etc. In other words, we are sampling. right? We've just sampled ft, sorry, by doing that, right? So this is the explanation here. So you take the key to it, of course, is this: to sample, right? Sampling, right? You must multiply by the comb function, right? You must multiply. That's the key to it. If you add, you're not going to do anything. The key to it is that, the multiplication. So you take any signal and you multiply it by the pulse train. What is a pulse train? A series of impulses uniformly spaced in time. Then what is going to happen? You're going to sift out the values of the function xt. You're going to sift out the values of the function xt at uniform spaces in time, the same spacing that the impulse train or the comb function has. In other words, you're going to sample the values of the function. And in a diagram form, this is what it looks like. You take the function and you have a multiplication, what do you call it, system, whatever that system happens to be. And electronically, we could do it, right? That's not an issue. But you have a multiplication process, I should say. And the multiplication process takes the pulse train, multiplies it by the signal, and you get this series of samples coming out. So the signal is continuous, which is xt, that they want here. You take the sample, train the comb function uniformly spaced, and what you're going to get is that you're going to pick out the values, and the actual values you have, all right, the actual values you have are here, 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 here. Right, so those are the values. You have sampled the signal. Okay? And electronically, we saw one version of creating that electronically was electronic switch. So you have the switch and you have a storage element. All right. So the switch in effect is a pulse train. The pulse train is turning the switch on and off. The capacitor is what is storing these values here. Okay, so conceptually, that is how it works. In reality, what they would do, and you know of devices, electronic switches, for instance, a field effect transistor, right? You can, if you bias, well, whether it's a N channel or P channel, you turn it on, the channel conducts. You turn it off, the channel is an open circuit, high resistance. So you can use that as an electronic switch for argument's sake. All right. Remember, as I keep trying to stress that whatever we're doing here are models for whatever the real world is doing. So any questions on that? We all right with that? Okay, as we're going to see later on, we will see it a bit in this course here. But if you do signal processing or you do some of the work in the microprocessor course next time, you're going to see that spacing here, T. We got a different color here. That spacing T, that is extremely important in determining how good a representation or how good your sample signal represents the real world. If you look at the diagram below here, you can see approximately that the spots, the sample points behave a little bit like what the real signal is looking like. If you were to sample, if you were to decrease T, in other words, T gets smaller, so we were sampling here, 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 in between here, you get these additional values. and you start to get closer and closer to what the real signal is looking like. All right, so there's a relationship between how good the signal, the sample signal is, and how good the real signal is, and that relationship has to do with T. All right, and there's a rule in general that what you want to do is that if you know some information about the signal, whatever is the signal, there's a rule about how fast you sample so that you at least represent the signal adequately. All right, and we'll talk about that. Yes, question.
Yes, there's one general question, right? So when you turn on the switch, when you switch it on and you sample that waveform and it's stored in the capacitor, right? And you take it back out, so that capacitor is storing that sample part of the wave, right?
Correct.
Does that capacitor have any effect at all on the waveform that we would have to account for afterwards?
Right, and all of that has to do with another series of things that we'll talk about, not here, but we may get it in electronics, and you will also get it in microprocessors as well. It has to do with the whole analog to digital conversion process. Yes, the capacitor has an effect. As you can imagine, if I take, let's say I store a value, just a little larger here. Right? So if the capacitor, for want of whatever the storage element, so let's say we're using a capacitor, it has this value here, right? Get a different color. So this is our interval T. So when we now start, we have the value here. Until we sample it again, the capacitor is going to hold this value, right? And at the next interval, it goes and it charges up to whatever is this particular value here. So that's a new value, and it's going to hold that for T again. How well it does this is a function of the capacitor and how the thing, which is what they call the analog to digital converter, how well it works. If the capacitor is not good, then between these two things, or if the circuit is improperly designed, between these the T point, the value is good. Right? So the next time you look at it, if you took the value, remember between these 2 points, the computer or whatever it is has to actually get the value. This is just a voltage here. At this point, this is just a voltage, some voltage, right? Between here and here, the computer or whatever it is that is going to use that value has to determine what the actual value is. If the value happens to be changing along a line, is discharging, then if the computer checks it here, certainly that is wrong. There's a difference between what the real value is and what the correct value is supposed to be, or what the measured value is, sorry, what the correct value is and what the measured value is. So all of that is part of the whole process, and we're going to talk about, well, we not here, but if you're doing the electronics course, we will talk a little bit about ADC and those designs to mitigate that kind of behavior. Yeah.
Okay, yeah, no problem. That was very thorough. Thanks.
Right, but what you have to remember too is that one of the things is that computer-based systems or electronic systems operate in usually operate in very short time intervals. So although I'm drawing T very large there, in a lot of systems, T is really, milliseconds or microseconds. So that the quote-unquote capacitor is actually an extremely small device. It's nothing that's going to resemble what you physically put onto a breadboard, right? This is actually a silicon capacitor, basically, which will be two little plates of silicon with dielectric between it that is embedded into a circuit, right? So you can't even see the thing. Incredibly small. The capacitance must be on the order of picofarads, but because the period of time that it has to hold the charge is on the order of microseconds, for that is a whole lifetime, So it's all a question of scale and context. Fair enough? And
Yes,
a lot
sir.
of words to answer, what what you asked. Okay. Okay, so let's look a little bit now about the discrete time version of the impulse. The discrete time version of the impulse is, this one is a physical thing that we create. It's something that is a value of unit of 1 at time at sample 0 at t equal to 0 and 0 elsewhere. So for instance, in our computer systems, say plus 5 volts. Right? If you have a plus 5 volt system, 1 here will be a 5 volt signal just for that instant, and then it's off. Some computers now work with 3.3 volts, so they want whatever is logic 1, voltage wise would be whatever is the voltage supply for it. And the same properties apply in shifting them around in time, right? So dn minus 3, and again, you could look at it as dn minus 3 t. If you want to remember, sometimes you remember I told you we put that t to remind us that in the discrete time world, things happen every capital T seconds kind of thing. All right? Right, so it is referred to as a unit sample or the unit pulse. This is important. Right, it is not a sampled version of the continuous time impulse. You can't sample the continuous time impulse because it's a function that is defined by its weight. But the actual time duration of it is supposed to be 0, so you can't sample that. And the same properties of shifting and sifting can be used to disassemble a signal, which is the reverse of what we just did, into a set of samples. So if I were to, like what we just did, we got to here, you remember, by taking x t and we multiplied it by the function, the Combs function. So what that did with us is to give us a series of the values, these points here. And those series of values, if you want to express each one of them, just like what we did before, this particular sample, for instance, is sample at n equal to 0 or t equal to 0. Here is at t equal to 1. So every time, and then if you go on the positive side, if it occurred at t equal to 1, then it means that this was xn by delta n plus minus 1, sorry. If it went negative, it would be n plus 1 and so on. The same properties that we had for the continuous time, we have for the discrete time, except that it is an actual value. It is a real tangible thing that we're dealing with now. It's not the undefined continuous time version. Yeah? All right, fair enough? And this is just a summary of what we just said. So this should be, this is the reverse of what we just spoke about. So you take a signal, you sample it, and you have a series of samples. What this is telling me is that I could take those samples, which are now tangible values, and I could break them up as a sum of, in shorthand, as a sum of individual impulses all over the place. Yeah? Yeah, no, maybe? Make sense? Good. Right, so let's talk a little bit now about these things. Something called piecewise continuous signals. The thing about it is that occasionally in the real world, as I mentioned before, the things that we like to measure, the voltages, the currents, the pressures, the velocities, and so on, are continuous time. They are occurring all the time. And as we saw before, there's a particular type of occurrence that we want, which is what we call causal. In other words, it happens when we want it to and nowhere else. Occasionally, however, things can happen. So for instance, if you're measuring or you have a signal, a circuit, sorry, and you have it on your breadboard, and one of the jumpers that is carrying information, you're measuring, let's say, room temperature. So you have a circuit board and you're measuring room temperature and so on. And one of the jumpers or the wires that is connected to the temperature sensor is not properly inserted into the breadboard. Okay? What happens is that you have this now, and you're measuring a nice signal coming in, and then the wire shakes. So you lose the signal, and then the signal reconnects again. This kind of thing is what you call a discontinuity. And what should be a nice continuous signal going in and out now becomes something called a piecewise continuous. So for the most part, it's nice and continuous, and then something happens and then it becomes continuous again. But at that point in time, you don't know what occurred. Right? We call that signal a piecewise continuous signal. And what it is mathematically is if you have at some point you have a value, and the value at some point in time t, if the value just before the time instant t and the value just after the time instant t are different, then you have a discontinuity in the signal. Of course, in like the case of the jumper, if depending on what it was, if the jumper wasn't totally out, it just for a brief instant in time it disconnected, and the signal for all intents and purposes, the value before and after were the same, then nothing happens. But there could be an instant where something happens to the information coming in, and because of the disconnect, both the unit being measured and the system that is taking the information, both of them have gone in different directions until the signal comes back in, and that is where you have this disconnect coming in. Those signals give us problems, and you need to, what we're doing sort of graphically here is to try to figure out what happens when discontinuous signals occur. There are some kind of signals that are intentionally discontinuous. So for instance, that square wave that we have down, which is a pulse train different from the impulse. We spoke about an impulse train a little while ago. This is a pulse train here because it's a series of pulses, right? And they're uniformly spaced apart, okay? So it's looking like a square wave or rectangular wave. So something looking like this, right? Or something looking like that. All of these things, these are pulse trains, and these are intentional. These are intentionally so, and they're what we call piecewise continuous because we know how many of these occurrences happen. Right, we are making the signal. So in other words, by whatever circuit or clock or whatever it is generating that, we know that, for instance, if the duty cycle of this is 50%. Anybody remember what duty cycle is? Came across that term before? Ever come across it? Duty cycle. No, well, not necessarily logic 1, but yeah, the first answer was more or less what it was supposed to do. The ratio between on and off, actually the ratio between the on time to the total time, right? So for instance, right, so you sort of partially had it there. If you look at this time over this entire time, oops, my mistake, let me clear that. I think I have a very bad pointer system on this, but anyway. So you look at this duration here compared to this duration here, right? So a 50% duty cycle means that this time is half of the whole period. 25%, this is a quarter of the whole period, and so on. Because we know that, we can design circuits to have, put in there, we can have this design circuits that have any kind of duty cycle that we like. Because of that, because that is intentional, we call that a piecewise continuous signal. Okay, so it is continuous, but it is intentionally, and we know that sometimes there's 1 or 5 or 50, whatever it is, and then for the remainder of the time, so if it's a 25% duty cycle, 25% of the time is 1, and 75% of the time is 0, and so we can go on. Those are piecewise continuous signals, so they're not quite discontinuous. We treat them as though they are continuous because we have designed them that way, right? And the issue with that is what happens now. Let me go back to the slide a little bit. So back to the question. So let's say this was this particular thing here. Pacemakers, you mean, not peacemakers. Yes, a pacemaker is something that would have pulses that happen at particular intervals at very frequent, at very, what you call it, predictable, unknown intervals. So yeah, they sort of circuit, the clock signal driving the pacemaker would be something like that, a piecewise continuous signal, absolutely. But back to your own pacemaker. So here what's happening. So you have a signal, and the signal is behaving like what we have on the screen. But in order to process that, let's say this signal is a velocity, Vt. So if that's a velocity signal, and I'm using this, like I'll come back to the pacemaker in a while. I'm using the velocity, so I'm measuring the velocity of, let's say, my vehicle, but I'm using that to determine the acceleration. So I have to integrate or to differentiate. I have to do something. So I'm using this velocity to, in fact, I'm using this I'm using this to determine distance. I'm using the velocity now to determine how far the car has gone, so that I could indicate on the dashboard that I have so much fuel, or if it's an electric vehicle, that the battery has so much range left in it. And I'm using the velocity of the wheels of the vehicle to do that. I have to differentiate to get distance. I have to take the differential of the velocity. So what happens now when I differentiate something looking like that? All well and good. Here I could differentiate as a strange looking function, but if I take the derivative, it's going to do something as a nice continuous function until I reach here. What happens at the discontinuous point here? Right? And that is where the problem with discontinuous signals come in. What happens at the jump, at the transition point? What is the derivative of that? And just conceptually, you have to bear in mind what happens with a step function. When I take the derivative of a step, what happens? From what we did last time, what's the derivative of a step? Nope. That's the integral of a step. Well, you really only have one choice, right? If it's not a ramp, then it has to be an impulse. Correct, right? The derivative of a step, remember what is the derivative? If you go back to first principles, a derivative is a rate of change, right? A derivative is a rate of change. So if I take the derivative of a unit impulse, no rate of change here. Here is going from 1 to 0 in 0 time. So what is that? A rate of change of a unit in 0 time is an impulse, right? In this case, from 1 to 0 is a negative going impulse. When you find a derivative, when you start to find the derivatives of discontinuous signals, every time the signal jumps from one value to another, that is a sudden change or a step change. So at this point in time, it had a value, and then it suddenly changes to another value here. If you're doing some calculation on that that involves like a derivative, that is going to give me an impulse, in this case a negative going impulse. If it is the other way around and it jumps from a low value to another higher value, and you do a derivative of that, it is going to give me a positive going impulse. Yeah? Fair enough? Right, so what I will do, the rest of the lecture here, we will finish off tomorrow and talk about some examples and specifics. If you look at it here, we have some examples to work through, but conceptually now, it's very easy to understand how it works. If I wanted to find the derivative of that signal, all you have to do now is to look at the points where the signal is discontinuous. Every time it suddenly changes, it is going to have an impulse. And in between where it's continuous, once it's continuous, we could find the derivative of it, whatever the function is. If we know the function, it's just a calculus function. But the test of it is what happens at these points here. Okay? So your homework would be to read the rest of the slides here. There's a few, about 3 slides on that. And tomorrow afternoon when we meet, we'll run through it just to make sure everybody gets a shorthand and actually do a couple of rough examples and then go on to the other part of the discussion. Yeah? So any questions before we close off? All right, so think about it. Think about it, and when we start up tomorrow, if you have any questions based on what we discussed today, at the start of the class, we'll take those questions, clarify it, and then we go ahead. Yeah? Okay, so if that is the case, let me stop the recording now.